Right, so now we're going to take a look at something a little bit more complex. We've been looking at plenty of complex things, in fairness, but this is something that kind of gets us to the last step for questions that regularly, but not always, show up on the AP exam. And the biggest thing about this is we're going to be looking at a circuit, but then we're going to be flipping some switches to change that circuit and predicting what's going to happen to each of these things as a result. So this is one of several videos where we're going to look at several different samples of this, and we're going to connect them with real life so you can see it happening in real time. At least that's the goal. Now, a common thing on the AP exam is, and we're going to try and do the same thing here, is we're going to say that all the resistors are going to be the same resistance. Now, there's one thing that I want you to realize about this. I've mentioned it a couple times, and here's where we're going to start to see it. All of the values, when we start switching things out, a bunch of the values for the circuit are going to change on a regular basis. I can't guarantee that. It depends on how you change things. But for the most part, you should be prepared that almost everything is going to change. In fact, the main things that won't change, at least for our treatment of the ideal scenario, is with an ideal battery, the total potential difference for the circuit for the batteries is going to stay the same, because that's something that is actually spec'd for these. These are a 6-volt battery, having the two of them together, or the two power packs, I should say, 4 AA's all together. And then each of the physical resistances of the light bulbs are all kind of a set value. So here's what I'm going to do. I'm going to complete this circuit. I left that little part out. But nothing is on right now because I've built in 2 switches in the paths. So we've got, this is actually the negative end of the battery, just the way that I've got this set up, but neither here nor there. We'll say that charges are coming out of the battery, going through the light bulb here, and then they split off to each of these branches and come back together here. So if I were to draw this diagram, I would have something like this. Got a resistor here, a resistor here, and a resistor over here. Great. Now, technically, I've flipped my battery, but for our purposes, that's not going to make much of a difference. Doesn't matter if this is on this side or that side. Oh, you know what I should actually do? I should draw them in with the extra parts that we've got. I've got 2 switches. One right here, and one right here. Great. And they are both open right now, which means our circuit is off. The switches are open. Here's what I'm going to do. I'm going to close one of the switches. I'm going to close the outside switch. So right now, the circuit isn't doing anything interesting at all because there are no paths. We do not have a complete circuit. This is an open circuit. I'm going to close part of the circuit by closing this switch. And we see now we've got an outcome. And I do want to emphasize this. When I flip the switch, both of them go off at the same time, and both of them come on at the same time. It's not because we've got a little charge marching out here, and it gets here first, and this one comes on first, and then this one comes over here, and then this one comes on. No, they come on at the same time because there are charges all throughout this. I could also switch this out, no pun intended. Let's see. Put this over here. This is a little different, but I flip the switch, all of them come on and off at the same time. I could remove this and replace it with just a wire and we'd see the exact same outcome. Now, we'll play around with that one a little bit later, but I wanted to try and keep this kind of simple where we've basically only got the 3 resistors. A lot of times they'll ask you about 4 of them. We'll take a look at some more complex circuits as we go. All right, so I flip the switch. What we've got is this is now closed, and we've got current that is coming out of the battery going through, let's call this one resistor A, this one's B, and this one's C. The current goes through resistor A, down through C, and back over to the battery, and with a cursory glance, hopefully you're getting used to applying Kirchhoff's rules without having to write everything out. The current that goes through A is the same current that goes through C. They are both in series, and this other branch might as well not exist because I've opened the circuit there, opened the switch, so no charges can flow that way. So the current through A has to be equal to the current through C. And because our power can be expressed as I squared R. There were 3 different equations that I gave you, but the reason that I bring this up is we're going to compare the current going through each of these resistors and their resistance. But if their resistance is the same, that means whichever one is getting the most current is going to be the brightest. But since both of these have the same resistance and both of them have the same current, they are, lo and behold, the same brightness. Now, instead of flipping the switch on and off, another way that they describe this on the AP exam is sometimes they'll unscrew the light bulb. And when you do that, you're basically breaking the circuit because the charges go into the light bulb, come back out the other side, and so if we remove it, it does not complete the circuit. So just as a heads up, in case you see the unscrew a light bulb, that basically means that they're flipping a switch, opening that part of the circuit. They're breaking that part of the circuit. If the light bulb is removed, unless it is replaced with a wire, it won't conduct it. Then no current can go through that branch. Great, now that we've got that, we've got a prediction as to why these two appear to be pretty much the same brightness and everything that's going on. Here's where we get to the new stuff. Now we're going to say the following. I'm going to close switch B. And we want to know, let's predict what's going to happen to the power of A and the power of C. In other words, these are light bulbs, and their power is a direct relationship to how bright they are. So I want you all to predict what's going to happen to each of these bulbs when I close this switch and open up another path for charges to go down. Okay, well, common thing that people think is, well, we'll still have the current going through A, so A would stay the same, but some of it's going to go to B and some of it's going to go to C, so C is going to get dimmer. That's a great way of thinking about it. So I'm going to flip the switch. Here we go. Let's watch C. C definitely got dimmer. But there was another thing that I mentioned in there, and it's a common mistake that people have. All of the current is going through A. Watch what happens to A. It gets noticeably brighter. This is something that is not always predicted by students. They can usually tell what's going to happen to C, but they don't necessarily know what's going to happen to A. Let's talk about what's happening to A. Okay, and for this, let's go back to what I had mentioned before. The best way that I've found to think about these circuits is to think about them as people trying to get out of the gym. So we've got a bunch of people going through one of the doors here, and then when we close this switch, we're opening up another door. What does that do to the total number of people getting out of the gym? If I open more doors, then more people get out of the gym in a given time. Remember, when you're describing the gym, when you ask yourself how many people are getting out of the gym, what you're actually describing is the total current. How many charges are getting out of the battery? I've opened another path, making it easier to get through the circuit or to get out of the gym, if that's how you'd like to think about it, which means my total current goes up when I close the switch next to B. Now, this is tying into stuff that I mentioned before. Two resistors in parallel are always going to have a resistance lower than any of the individual ones because it's always easier to get through. Even if one of the resistors is really hard to get through, it's an additional door that's open. The equivalent resistance of this section is less than if I don't have B in there. And that means that it is easier to get through the circuit and our total current goes up. And all of that increased total current goes through A. Well, if the current through A goes up, then it will get brighter. By the same token, if I open the switch here, I'm closing a door, making it harder to get out of the gym, so fewer people get out, our total current goes down, but all of it is going through this resistor, which means since our current goes down, it gets dimmer. Why does this one get brighter? Well, because we closed off this branch, so even though it's less current overall, all of it has to go through here. When I when I close this switch, opening another branch, now we have even more current, but half of it's going this way, half of it's going this way. So this one still ends up with less current overall. They join back up here and go over here. So this is a way that we can start predicting what's going to happen with the switches. Well, what happens if I were to open this switch or remove this light bulb? Well, that's closing this door. And that means that fewer people get out. We have less total current, but all of it goes through here. So this one gets dimmer. But now, since this path has been shut down, all of that lower current all of it must go through here instead of being split, so this one gets brighter. The best way to work with these is to think about the gym aspect. You're opening and closing doors. What's that going to do to your currents, and where are your currents going? In the usual case that they provide, if all the resistors are the same, then thinking about the current will be able to let you predict which ones are going to be the brightest. All you have to ask yourself is this: what's happening to the current? Does the current get bigger or smaller? If it gets bigger, the bulb is going to get brighter. If the current gets smaller, the bulb is going to get dimmer. Great.